Hello, my name is Ian Pena, and this is Physics 2212, Lab 5, Faraday's Law. So the purpose of this lab was to study the magnetic induction as well as the eddy currents produced by dropping a bar in an aluminum tube. And we did this by analyzing the computational data and comparing it to the experimental data found in lab. So we used the following principles. We used Faraday's law, which basically says that a change in magnetic force actually is equal to an induced voltage. We also used Biot-Savart's law that says that a induced current or a steady current creates a magnetic field. And we also use Newton's second law that change in momentum over change in time is equal to net force. So to preview our data in lab, we found that the magnet was able to fall through the aluminum tube on average in 1 minute and 32 seconds. And when doing the observational model, we had to neglect air resistance as well as friction when the magnet hits the tube. And in this experiment, our magnet and aluminum tube were the system and everything else was the surroundings. So in our experiment, we used a tube with a length of 0.46 meters and a width of foil of 0.002 meters. It had an inner radius of 0.0155 meters, so a total radius of 0.0175 meters. The mass of the magnet was 0.023 kilograms. And on the first time, we recorded a time of 1 minute and 36 seconds. The second time was 1.36 seconds, and the third time was 1.25 seconds for an average of 1.32 seconds. So this is the computational model that I used in my lab. In these two portions of the code, we find the magnetic dipole as well as the change in magnetic flux. In these lines of code, we are basically deriving the forces that are acting on the magnet, force of gravity, as well as the magnetic force on the magnet. And we are combining these forces to get the net force acting on the magnet. And with this net force, we can derive the velocity of the bar magnet as well as the position of the bar magnet. And this is the graph and model that my code produced. The velocity should be in the negative direction as the bar magnet is falling down. The possible sources of error that could contribute to our discrepancies within our results could be from the human error of stopping the stopwatch in the exact moment, as it's kind of hard to do. The air resistance that we neglected did actually have an effect on the magnet falling through the tube, as well as a possible force of friction when the magnet scrapes on the side of the tube. So for the what if and why questions, so what if the resistivity of the conductor was reduced as close as possible to zero? So using Ohm's law, where V equals IR, and if R is decreasing, then the current would actually increase. So this would cause the bar magnet to fall slower, as there would be a greater current, resulting in a greater magnetic force. And then what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So with more holes and slots in the tube, that means there will be less induced rings. And with less induced rings, we would have less of a magnetic force, and magnetic force is the force counteracting the force of gravity. Therefore, the bar magnet would actually fall faster down the tube. Thank you for watching my lab.